Hello, this presentation is titled Raku RAG Demo and Semantic Nearest Neighbor Graphs. My name is Anton Antonov. Today is September 18th, 2024. So RAG stands for Retrieval Augmented Generation. It's one of the primary use cases for large language models. We're going to use the so-called LLM embeddings to demonstrate the semantic similarities that can be uncovered using LLM embeddings. And with LLM embeddings, we can do actual retrieval, and then the generation can be augmented with the text corresponding to those vectors. So this is what this demonstration is about. I have 3 graphs to show, but I'm going to go into detail only with the first example, which is a very simple collection of just words, not documents or not large documents and texts. And ideally, it's going to be convincing. This example is going to be convincing, but semantic similarities can be uncovered using these technologies. The second and third example, I'm just going to skim over them. I don't want to make the presentation too long. All right, so with the words, I'll go back to this diagram here, but let me actually just narrate what's going on here. So I have this 20 words, like angel, apple, aardvark, cookie, cow, devil, film, and so forth, right? And I'm going to use Gemini and find the corresponding embeddings. This happens with this function, create semantic search index. I have this, so this is what we get. So Gemini produces, this particular model of Gemini I'm using, it produces vectors with length of 768 length. These vectors, when they are in the database, they are actually stored in this C arrays. We have to use C arrays in order to have fast computations here. Now I'm going to find this vector for the word coffee with the same configuration. So I have the same length, vector of the same length. I'm going to find the nearest neighbors of this vector, meaning coffee, into the already created 20 vectors, right, in this database based on the words. And those words are chocolate, cat, and cookie. I mean, I can see why coffee is connected to chocolate and cookie. I'm not sure about cat. All right, so here I'm finding 2 nearest neighbor graphs. One is with 1 element, 1 nearest neighbor, right? The other one is with 2 nearest neighbors per vertex or per word. And so I'm going to show why I'm doing this. I'm finding the connected components over the first graph with 1 nearest neighbors, and let's actually show it. So basically, these are the connected components, and I have selected the largest component here, and so we can see how projector, Bible, film, Apple, movie are connected. So I assume Apple and film are connected because of Apple, the company Apple makes movies and films or whatever. Now, Bible, movie, projector, yeah, they seem to be connected. If this is not exactly clear, let's examine some of these simpler components, right? Like tiger is connected to cat, right? So if we have 1 nearest neighbor, the word tiger has 1 neighbor, cat, right? And cat has 1 neighbor, which is tiger, right? So, okay, makes sense. Same with angel and devil. And raccoon and aardvark. Now here, this with tree, house, and so forth, it's actually interesting. Let's actually examine this line graph here. And so we can see that, say, tree can be connected to house, right? We can use trees to make house, so we have tree, house. Now house and car, they might be connected in images, in discussions, whatever. Car and horse are connected. The horse can pull the car, and cow and horse, well, they're these large mammals, right? And so this is how this semantic similarity works for this particular model. I'm not saying this is the only semantic similarity that can be uncovered, but with this particular model I'm using, this is how it is being done. If I use the graph of based on 2 neighbors, right, it's a little bit more interesting. Now, the cow has not just 1 nearest neighbor, because I said that I want to use the graph with 2 nearest neighbors, right, semantic nearest neighbors. We assume they're semantic because we're using the LLM embeddings, right? So cow is connected to horse and to a cat, and similarly, tiger, cat, aardvark, raccoon, they're all connected. All right, so if we look at, say, cherry and plum, they're fruit and they're connected to apple and cookie and so forth. We also see how angel, devil, and Bible have this kind of click here. All right, so basically this is the example. What was the first example? What I was showing is that we select some words, we get these embeddings. We can use any model, right? And so, for example, I used only Gemini, but say OpenAI, if I use some of the ChatGPT models, they produce larger, bigger vectors. And so after that, we have found the nearest neighbor graph with one neighbor, and then with two neighbors. We find the connected components of this with one neighbor and make a graph plot. Hopefully it's pretty clear what's going on. Now here I'm going to ingest the vector databases I have created well, recently, but you can see the vector database I was discussing earlier is just created just now, right, with 20 words. So I'm going to select two of those vector databases, going to ingest them here, and so I'm going to show. So the ingestion is slower because it's in JSON. These are representative JSON. They're like dozens of gigabytes each, and I need to basically make a faster ingestion. It is expensive and slow to compute the vector databases. That's why we export them, and we have a streamlined way to export them to a local folder, to a disk, and then retrieve them. And so you can see here a sample of the vectors. You can also see a sample of the actual text behind some vectors. It's not the same vectors here, but it's similar thing, right? Basically, the vectors have some IDs, and the corresponding texts, they have same IDs, and basically see a sample here. All right, so I'm going to merge these two databases into one larger database, and you can see the new name is number 833 and 447, right? So these two have been connected or joined, merged, and we have this 724 elements all together. I'm going to find the nearest neighbor graph. Again, it is important to have fast computations because these are large, dense vectors. So the typical algorithms for finding fast nearest neighbors that work in low dimensions, they're detrimental actually to use for this kind of large, dense vectors. So something else needs to be used, and that's why they were stored in C arrays. All right, so let me find the components here, top components, and let me show here a graph. Okay, so I think I need to zoom out. So this here is a semantic graph, right? It's very similar to what I did with words, but here we actually have texts or paragraphs or discussion points, right? Questions and answers in some podcasts. So this is with this larger graphs, and this larger graph, and I have colored the top components, the longest components, in this graph. All right, so my next example is actually going to focus on one of these databases, right? This is the podcast number 833. And so we can see here some sample. Again, I'm finding again the nearest neighbors, and I'm the nearest neighbor graph, and I'm also constructing the corresponding graph. It's smaller, finding the components again. I mean, I can show some elements here, but what is interesting here and what I'm going to show is what, let me zoom in. So here I'm making a function which LLM function, which takes a bunch of texts, right, and it summarizes them. It makes like a shorter title or a sentence corresponding to them. I mean, I imagine that I want to see the semantic similarities in this text, but I don't have the time to listen to the interviews, and I don't want to observe, or read everything. But I do want some kind of summaries to be shown, and so here with this component 5, I'm summarizing it using this LLM function. So this fnamer, right, goes to, I think it goes to ChatGPT actually, and produce this summary about string theories, mistreat others, like real achievements in physics. Okay, whatever. But it is about this. We can say that this component, the text corresponding to this IDs, were about string theory. And so here I have found the titles. Okay, I'm going to find the titles of the top 6 components, top 6 meaning the longest components. So we're here, and I think, yeah, okay, so this is the interviewer with Modern Wisdom, which I think is Chris Williamson, the name of the guy who makes Modern Wisdom, and probably they're discussing Joe Rogan. All right, and yeah, there's some kind of string theory related things and whatnot. And as I said, there's some, because of the wide variety of topics, we also see some political topics being discussed here. All right, so here I'm doing some relabeling and some in order to make this graph a little bit more compelling. So let me actually zoom out. And so here the components, they're not just uncovered and colored, but if we hover over this these points here, these titles, these summaries, they're actually going to pop up. And this particular thing, that's very suitable. This particular orange colored component is about, the current politics in USA. If I go for the brown one, maybe this is about string theory. Yeah, all right, yeah. So, and so forth, right? And so, okay, hopefully this actually somewhat convinces us that semantic similarities can be uncovered in this way. Now what I'm going to do is I'm going to take this component 5, right, which is basically component 5 is this. From the components which I found above, this in brown, these are the 128, whatever it is. So basically these are the elements of this component 161. Maybe this is, the tooltip is too small to see, but this the tooltip says right now what it says is 161.0 string theorists are criticized for lack of achievements, right? Okay, and okay, so here I'm going to take this component 5 and I'm going to do an actual retrieval augmented generation. Yeah, so the components have been taken. I have taken the corresponding texts here with this, and let me actually show this. Yeah, and so let me do C4, right? And I have joined them, right? Joined these chunks of text. You can see a very large text, and I'm asking summarize the following text into a list of 3 or 4 points, each which each with no more than 8 words, right? And this is more or less what we got. Foreign students are irrelevant theories, very interesting. String theories suppress competing theories, and I guess these physicists are being criticized for their behavior in string theory and so forth. All right, this was it. Thank you.